Okay, we appear to be live. Um, bigger. Even bigger. Okay, so let's see. If you're not already registered, need to email Megan like right now. She'll probably go home at 5. So like today is technically the day that you need to be entered in the system, or at least like the powers that be need to know that you're trying to get yourself entered into the system. And so if you have not already done so, definitely email Megan before 5, so that at least there's like a record of you attempting to get into the class. We'll talk today about probability distributions for discrete random variables, picking up where we left off last time. And so also picking up where we left off last time. It's Columbia. Parents have a conflict of interest that you should be aware about, even though we're still not talking about Stan today, but we might a little bit next week. So I can never have too many conflict of interest disclosures before that happens. Questions? Okay, so Tuesday we were talking about the Bernoulli distribution, which is a probability distribution defined over a sample space that just contains 2 isolated elements, 0 and 1. And what we've been talking about with these functions that return probabilities, they actually have a special name that was referred to in the reading and elsewhere, known as a probability mass function, or PMF. And the probability mass function for the Bernoulli distribution is given by pi raised to the power of x multiplied by 1 minus pi raised to the power 1 minus x, where again, x can only take 2 values, 0 and 1. So if we raise pi to the power 0, that's just going to be 1. So one of these 2 terms gets raised to the power 1. The other term gets raised to the power 0. And so probability of x given pi is either pi if x is 1, or it's 1 minus pi if x is 0, 1 minus pi being the probability of failure, where 0 represents failure, 1 represents success. So the Bernoulli distribution has this additional parameter, pi, which may very well be unknown, something that we'll ultimately try to estimate. But because it's a probability, it's confined to the space between 0 and 1. And these, almost all of these probability distributions are going to have these parameters in Greek letters that the probabilities depend on. And we also saw last time we could take the expectation of any distribution or any discrete random variable x by doing a weighted sum, a probability weighted sum of the sample space. And that's particularly easy in this case because the sample space only has 2 elements, one of which is 0. So we can multiply 0 by the probability of failure, get 0, and multiply 1 by the probability of success and get the probability of success. So we see the expectation of a Bernoulli random variable is pi. Again, expectations of discrete random variables are going to be real numbers. They're not in general going to fall inside the sample space of a discrete random variable. So 0 and 1 is, it's never going to come out pi if pi is interior to that interval. Nevertheless, pi is the expectation of a Bernoulli random variable. So the expectation is not, what you think is going to happen. It has a specific mathematical probability definition of, this probability weighted sum of the sample space. Also, we can easily get the variance of a Bernoulli random variable, remembering that we showed on Tuesday that the variance can be expressed as the expectation of the square minus the square of the expectation. And in this particular case, where the sample space is only consists of 0 and 1, the square of that is just equal to x. So if x can only be 0 or 1, x squared is equal to x in this case. So expectation of x squared is the same as the expectation of x, which is pi. And then we subtract off the square of the expectation, which is pi squared. And you can factor that to get the variance as pi times 1 minus pi, or success probability times failure probability. That is the variance of a Bernoulli random variable. Everybody see how we did that? And the Bernoulli distribution is really the only one that can be used in this very common case where the outcome you're considering is just success or failure. Did you vote or did you not vote? Did you get a job or not have a job? Stuff like that. And so in that case, like a logit model or whatever, we're going to be, and we'll get to this in a couple of weeks, but we can write pi as some function of predictors. And so if pi is a function of some predictor z, we could write this in an expression that, maps some, alpha plus beta times z to the 0, 1 interval. So it's appropriate to interpret it as a probability. And then we can use this Bernoulli distribution for our observed outcome, whatever that may be, as long as our observed outcome can be, classified as success or failure. So we'll be getting to that. But the Bernoulli distribution is very useful, and it's really the only distribution for this sample space. All right. So binomial distribution is related to the Bernoulli. A binomial random variable is defined as the sum of n independent Bernoulli random variables, each having the same success probability pi. So for a binomial random variable, what would be the sample space? Huh? 0 to n, right? So it's a count of the number of successes. What you'll see a lot happening is that you take one distribution and then you add, okay, what's the distribution of the sum of two or more? What's the distribution of the difference? What's the distribution of the product? What's the distribution of the ratio? And so we can form a whole bunch of other distributions by taking a distribution we know, like the Bernoulli, and then, asking, okay, what's the distribution of the sum of n independent Bernoullis? That's going to be binomial. That's going to have a sample space of the integers between 0 and n inclusive. So what would be an expression we could use for the expectation of a binomial random variable? Yeah.
N choose k times the probability of success to the n times the probability of failure to the n minus k.
No, although that's something. In this case, right. Well, we want, yeah. So getting ahead of ourselves a little bit. What would be the expectation, which is just going to be like a much simpler number than that? Close.
Pi times n.
Right. So the success probability times n, which I assume you came to that conclusion based on what we did on Tuesday, that the expectation of a sum is sum of the expectations. And so we're adding n Bernoulli random variables. Each of it has a expectation of pi. And so we do pi plus pi plus pi plus pi n times. That's n times pi. The expectation of a binomial random variable. And then what is the expression for the variance of a binomial random variable? Utilizing another result that we came to on Tuesday pertaining to the variance of a sum. Yes. And how did you come to that conclusion? Based on what up? based on the Bernoulli. Care to elaborate? Does anyone care to elaborate for him? So what we said the variance of a sum was last time. Did I dream this? Patrick.
Was it the sum of the two variances plus the covariance, or twice the covariance?
Plus twice the covariance. So we know the sum, the variance of a Bernoulli random variable, which we're going to be adding up n of them is opposed to just 2. But so what do we do with the twice the covariance piece? They're independent, so is 0. Right? Covariance is a measure of linear dependence. Independent random variables have no dependence, linear or otherwise. So yes, the covariance of independent random variables is 0. So we don't have to worry about the 2 times 0 business. All we have to do is sum up the variances. And we just got through saying that the variance of a Bernoulli random variable was pi times 1 minus pi. And if we add up n of those, we get n times pi times the quantity 1 minus pi. So you see how we can build distributions and build understanding of those new distributions using old distributions and applying just, arithmetic operations to them. So now we get the question, what is an expression for the probability mass function, probability of x given pi, if n is 3, to make it a little bit easier on you? And to make it even easier on you, there is a hint that there are 8 cases which you need to consider.
The 3 choose x times pi to the x times 1 minus pi to the n minus x, 3 minus x?
Yes, I believe it would. But just to spell it out in a little bit more detail. So 2 of the cases are all 3 succeed or all 3 fail. They're independent. So it's just pi to the 3rd or 1 minus pi quantity cubed for the case where all 3 fail. So that gives us 2 cases. Then we have the case, well, 1 succeeds and 2 fail. So that would be pi trivially raised to the power of 1 times 1 minus pi raised to the power of 3 minus 1 or 2. But the 1 succeeds and 2 fails can happen 3 different ways. The first one could succeed and the last 2 fail, or the middle one could succeed and the edge 2 fail, or the last one succeeds and the first 2 fail. So there's 3 different ways to accomplish that. So we're now up to 5. Or we can have 2 succeed and 1 fail. So pi squared times 1 minus pi. And 2 succeed, 1 fail can happen 3 different ways. The failure could be first, middle, or last. So that gives us 8. And if we were to write that all in one expression, which has now been said twice, the general form of the probability mass function for a Bernoulli random variable, depending on the success probability pi and n, the number of tries, is n choose x times pi to the x times 1 minus pi raised to the quantity n minus x, where this expression n over x with no fraction bar in the middle of it is universally known as the choose function or the binomial coefficient. It can be expressed as n factorial divided by x factorial divided by n minus x quantity factorial. Again, the factorial function for integers is just like x times x minus 1 times x minus 2 all the way down to 0 or down to 1, and 0 factorial for mysterious reasons is defined to be 1. Questions about that? Patrick?
Like any intuition for the end, because like the right half is like the probability function from earlier. Is there an intuition for the n choose x?
Yes, there is. N choose x is the number of ways in which x entities can be chosen out of n if the order of them is not important and ignored. So we got like a whole bunch of you here. If we were to do like a whole bunch, choose 5, how could I select 5 volunteers out of you? How many different ways if I could do that if I'm not distinguishing among the order in which those 5 are chosen? So that's the definition of it. You choose to find that intuitive, all the better. But if you don't find it all intuitive, just like take a small number of things and count up the way where you can choose some subset of them. And that will be equal, if you do it correctly, to whatever this function evaluates to. Other questions? Okay. So back to bowling. One might try to come up with or try to use the binomial distribution for the first roll of a frame of bowling where n is 10. But why would that be completely inappropriate? Heinrich.
For 2 reasons. First of all, I think every individual pin would have a different probability of being knocked down. And then also, say pins that are closer together would have they would basically be dependent. Like the one standing behind the other pin would have a higher probability of being knocked down than the first one.
Right. Certainly they aren't independent of each other due to their spatial, and that's like an important metaphor for a lot of things that we want to do in social science. You might have to consider where people are living and how they're grouped together and stuff like that. So that was one reason why it'd be inappropriate. And it may very well be the case that like the pins in the middle have a higher probability of being knocked down than the ones on the edges. The bowler is aiming for the middle. So they might not have the same probability either. So no. Could a Bernoulli distribution be used for the probability of successfully getting a strike? What do we think about that? Right. So we're sort of changing the event from single pins to all 10 pins collectively. And then, yeah, maybe you might have to make the success probability a function of like the ability of a bowler or something like that, but you could do something along those lines. Could the Bernoulli distribution be used for the probability of knocking down the frontmost pin? Why?
Same reason.
Same reason, except now the event is just a particular pin. Right? Could knock it down, not knock it down. So if we let xi be the random variable that's just yes or no, is pin I knocked down, and pi I is the probability of knocking down that ith pin in a Bernoulli distribution, what conceptually would be the expression that we have here? Probability of x1 given pi 1 multiplied by the product of the conditional probability of the ith pin getting knocked down given its success probability and the realization of all previous pins being knocked down. Again, this symbol here, if you're not familiar with it, indicates multiplication. So we had like the sigma, and that indicated summation, which we've done many times. This is an analogous thing, except it indicates multiplication. So a product of these things. So we have a product of a Bernoulli, set up for the first pin, multiplied by conditional Bernoullis for the subsequent pins, given that the previous pins were or were not knocked down. So what does this expression collectively yield us? As a concept. Ryan?
Evaluate 10, would it be the probability of getting a strike on your first roll?
Right. Or a little bit more generally, so yes, you could evaluate that for 1, 1, 1, 1, 1, 1, 1, and it yields you the probability of a strike. But even more generally, where some are ones or some are zeros, this is an expression for the joint probability of knocking down some pins and not others. Because we have marginal times conditional. So marginal probability of knocking down the first pin times conditional probability of knocking down the second pin, given that you did or did not knock down the first pin. And so what's marginal times conditional? Joint. So that gives us a joint probability distribution for the first two pins, multiplied by a Bernoulli for the third pin, given that the first and the second were or were knocked down, the 4 combinations that could happen to the first two pins. So we have probability of 2 times conditional probability of 3. And so what does that give us? Right? Or a trivariate probability distribution. And then if we take that and multiply it by the conditional probability that the fourth pin gets knocked down, given that the first 3 were or were not, so 8 possibilities there, then what do we have? A 4-variate probability distribution. And if we keep doing that all the way through 10, so the 10th, given that the 9th, 8th, 7th were or were not knocked down, then we would have a joint distribution for what happens to all 10 pins on the first roll of a frame of bowling. And that would be a really complicated thing to say, like, what is the probability that the 10th pin gets knocked down, given that the 9th was and the 8th wasn't and the 4th was and the 3rd wasn't, all these sorts of things. But that would be the way to do it right if you were using Bernoulli distributions, rather than saying like all these pins are independent of each other and they have the same probability of getting knocked down. That seems a little bit ridiculous. But you could go kind of ridiculous in the other way of specifying particular probabilities, conditional probabilities, that the 6th one gets knocked down given what happens on the first 5 or whatever. And you can multiply that all up to give you a joint probability for what happens on that roll. Questions about that?
Sorry, I'm still a little bit confused in terms when you say like you have the marginal of the first row times the condition of like given x1 and you are conditioning on that that's x2, so that's the kind of joint probability of row x1 and 2, right? And then you just keep on saying I have this as like a marginal for 1 and 2, and then I condition on that with 3, so that's just like the joint probability of the first 3 rows, and just keep iterating. Is that how to understand this expression? Okay.
Yes, that's exactly right. So this product thing, okay, so first we start with the marginal probability that the first pin gets knocked down or doesn't, success or failure there. Then multiplied, starting with I equal 2. So we're just going to not have any of this. Just the probability that the second pin gets knocked down, given its probability, and given the fact the first pin was or was not knocked down. Those two things together form a bivariate probability for the first two rolls. And then we go to I equal 3, multiplied by a Bernoulli setup, given the first two pins. The product of those three things gives us a trivariate probability. We go to I equal 4, multiply one more. Now we get a quadravariate probability thing. Keep going all the way to 10. I don't know what the word for it is, but it's a joint probability for what happens to all 10 pins that we've composed by marginal times conditional times conditional times conditional 9 times. Changing possibly the success probability as a result of what we condition on. That's the spatial layout thing. So the pin in the far left corner is probably independent of the pin in the far right corner, or mostly so. But yeah, like the ones right behind the front pin. So it goes 1, then 2, then 3, then 4. So if you're right-handed and you hit the front pin, the one behind it and to the left is likely to fall down, etc. Everybody got it?
I guess I'm just this is like the we have the 2 given the 1, the 3 given the 2, but I mean technically does this have to then go across every permutation of them? Okay.
Yes. So when you specify the probability the second falls down given x1, you need to consider the case where x1 is 1 and the case where x1 is 0. And when we do it for the probability the third gets knocked down given x1 and x2, there's 4 branches that we need to consider. For the first could be success or failure and the second could be success or failure.
X1 can be any.
No, literally the first one.
Okay, that's what I wanted.
Right. So yeah, you want to put an ordering to the pins, but they already have an ordering, so you might as well use that one. Other questions? So now let's learn about another distribution. So what if we let the n, the number of trials, go to infinity? Well, if we fix the success probability and let the number of trials go to infinity, we're just going to have an infinite number of successes. And that's not so interesting. So as we let n go to infinity, let's let the success probability go to 0. It's such a perfect rate that n times pi remains constant. So n is getting big, pi is getting small, but the product of n and pi remains the same as we do this process. And n and pi is the success, is the expectation of a binomial. So we'll just call that mu. So what happens under this limiting process to the binomial probability mass function is we let n get big and pi get small? Well, 1 minus pi raised to the n minus x can be broken up into 2 terms, the n and the minus x. And the only thing that's really hard, or it's not hard, but you may not be aware that this is the case, is that 1 minus mu over n raised to the power n. The limit of that is n goes to infinity, is one of the ways to define or characterize e to the negative mu. There's lots of ways to define e, the number, and they all are equivalent definitions. It implies 2.7128, etc. Anyway, this limit of that first term there is e to the negative mu. And then we have 1 minus mu over n raised to the power of negative x. Those are all constants except for n. So as n gets large, mu over n goes close to 0, and that just becomes 1 raised to the power of negative x. So that's 1. Then the other piece, n choose x times pi to the x. Well, we can substitute mu divided by n for pi, because that remains fixed. And then we can take the n to the x, move it over there, take the x factorial, move it over here. So we just have to deal with the n factorial divided by n minus x factorial. And so n factorial is like n times n minus 1 times n minus 2, etc. And then it gets to n minus x, and then n minus x minus 1, n minus x minus 2. So the n minus x factorial is going to cancel with most of the terms in the n factorial. The ones that are left over are n times n minus 1 times n minus 2, etc., to n minus x plus 1. And so the numerator is going to be a polynomial in n, where the leading term is n to the x. And then in the denominator, we also have n to the x. And so as n goes to infinity, that's going to approach 1 from below, leaving the piece on the right, mu to the x, x factorial. And if we combine those, we get the probability mass function for the so-called Poisson distribution, mu raised to the power x times e raised to the power negative mu divided by x factorial. That is the probability mass function for the Poisson distribution. And the Poisson distribution is defined for a sample space consisting of the non-negative integers, and consequently it's one of the core distributions used for modeling a variable that is a count. And it can be obtained by imagining this particular limiting structure on a binomial random variable. So again, assuming constant success probability and a large number of trials, each of which has individually a small probability of being successful, but collectively you're going to have an expectation of mu of them. And so that's another very common way we can take a distribution that we know, like the binomial, and ask what happens in the limit as something goes to infinity or 0 or 1 or whatever it may be. We get a new distribution that is applicable to a new situation, namely where we have an outcome variable that is a count. And, you know, there's nothing really that complicated here other than recognizing 1 minus mu over n raised to the power of n is the definition of e to the negative mu, which is not super important by itself, but then the rest of it, you know, just follows from taking some limits, and we get probability mass function. Okay. So what is the variance of a Poisson random variable? It is mu. And how did you know that? You just guessed it. You're a clairvoyant student. How could we not guess it? Oh, it's not a guess. Oh, you remembered it. How did you know it to be true when you took intro stats? You don't remember.
Why is it?
Why is it mu?
Is also the something else is also
The expectation?
yeah.
They're both mu. Right. So we already established, okay, what we really have here is a Poisson, or a Poisson is really just a binomial under a particular limiting process. And we know that the expectation of a binomial is n times pi, which we're saying is going to be fixed at mu. So the expectation of a Poisson is mu. Question becomes, why is mu also the value of the variance? And the answer to that question can be obtained not just by remembering that you memorized it before, but by thinking what's the variance of a binomial random variable, which we just got through saying. Which was n times pi times? Right. So the n times pi we already worked out is you. Thank you. And the 1 minus pi is pi goes to 0 is, and mu times 1 is, thank you. So the expectation and the variance of a Poisson random variable are the same number. It's going to be a positive number. And yet the expectation and the variance are always different concepts. They just happen to coincide numerically in this case. So I like to think of a Poisson as like an eclipse. The moon and the sun are different things. Very different things. Very different temperatures. Different sizes. All kinds of things. But once in a blue moon or whatever, like last year, they coincide in your field of vision. And like the birds go crazy and stuff like that. So the moon and the sun can coincide in your field of vision. The mean and the variance in this one case can be the same number. But they're different concepts, even if they happen to be the same number. And the fact that the mean and the variance are the same number is a like interesting fact. It's not actually a good thing for the purpose of applying this to a lot of social scientific situations, because a lot of times we find with count variables, empirically the variance is greater than the mean. And thus the Poisson distribution is not so appropriate for that. So because it only has one parameter, it has limited flexibility. But it does make it a very concise probability mass function. Not that that matters that much. It's already implemented on your computer, so it doesn't really matter how concise the probability mass function is when somebody writes it on a slide. But there you have it. Questions? So in a Poisson distribution, the mu very well be unknown, something we might want to estimate. And we can move on how to do that. So previously we used the ratio of Fibonacci numbers to give us a probability mass function for bowling. We can do the same sort of thing with the so-called Bell numbers, which you may not have heard about before. But the Bell numbers can be defined as the 0th Bell number is 1, the first Bell number also 1, and all subsequent Bell numbers are defined as the sum from 0 to n of n choose k times the kth Bell number. Bell numbers on their own are not super useful, but having this recursive definition allows us to easily write down a probability mass function involving the Bell numbers. And the Bell numbers, as you'll see, it's going to work out pretty well for us to introduce an additional parameter into our distribution for bowling. This guy here. And what is that letter? What alphabet does that letter come from? And what alphabet are you supposed to be learning? No. Is what? It is not lambda. One of my favorite Greek letters, upsilon. And so when defining a probability mass function based on the Bell numbers, we don't necessarily have to start at the 0th Bell number. We can shift the whole thing over, both x and n, by upsilon and still easily work out what we need to divide by in the denominator to make this a valid probability mass function. Namely, all the numbers are between 0 and 1, and they add up to exactly 1 over the whole sample space for bowling, which again is the integers between 0 and 10. So upsilon is an unknown parameter to us, but it can take on any of the non-negative integers. And so that space that upsilon comes from is known as a parameter space, because upsilon is a parameter. And the parameter space is often denoted by this Greek letter over here, which is Theta. 1 out of 2, not bad. So the parameter space theta and the sample space omega are similar conceptually. They're both sets. This case, omega, the sample space for pins, is the integers between 0 and 10, whereas the parameter space theta is the non-negative integers. So they're both sets, but one refers, the sample space refers to the set that the observable pin knockdowns can come from. And the other one, the parameter space, is where upsilon can come from. And so they're both sets, but we use different letters for them to distinguish a sample space of observables versus a parameter space of parameters that we would like to estimate. That's all. And if upsilon is an unknown parameter that is defined for non-negative integers, you could use the Poisson distribution with expectation mu to represent your beliefs about upsilon. And then you could update those beliefs with observed data on what happens on pins knocked down with various frames of bowling. And so this actually gets into using Bayes' rule a little bit, whereas we did something kind of weird the first couple of days with the bowling distribution based off the Fibonacci numbers. We pretended we knew the probabilities, you know, the ratio of Fibonacci numbers. We just, given the probabilities, we didn't know what was going to happen to the pins. That was a random variable. We knew the probability of them, but we didn't know the realization. Much more common for social science or science generally is to say we don't know the parameters, but we do know the data that were ostensibly generated by a data generating process involving one of these unknown parameters or maybe multiple parameters. And we want to see about estimating those parameters on the basis of data, in particular getting the posterior distribution of those parameters conditional on data under some assumptions about the data generating process. So you might ask, well, how would I choose mu in the Poisson distribution to represent my beliefs about upsilon before I see the data on this person bowling, especially considering that y'all didn't know really what upsilon was 3 minutes ago. That seems like a challenge. Oh, and we could implement what I said before with R code. You don't need to copy that down. The choose function in R is just in choose K. Okay, so what I was saying, how would I select mu in my prior that has a Poisson distribution for upsilon? And one way to do that would be to consider how the expectation for the number of pins knocked down in the first roll of a frame of bowling varies as a function of upsilon. And that is plotted here. You can see when upsilon is 0, the expectation is about 8.5. As upsilon gets bigger, the expectation for the first roll of a frame of bowling gets smaller. So we can interpret upsilon as a parameter that captures how uncoordinated a person is at bowling. And so you might be able to form beliefs about upsilon even before you start to see data. You just like look at a person and they seem like a 7 or whatever, and then you go over the curve down. You know, 50 might be a reasonable value of upsilon for somebody like that. And then the expectation, prior expectation is, you know, mu, you could use 50. But you need, you know, some way of being able to interpret the parameters before you can start expressing your beliefs about them. But, you know, you can always, or usually always, do that by seeing, okay, what is it that I might have a clearer understanding about, and how does that vary as a function of the parameters? And what I have a clearer understanding about is, you know, the expectation of the first roll. That's based on observables. And then, you know, think how that changes as upsilon gets bigger. And you, at least in one dimension, you can just do a plot for something like that. So we'll talk about other ways of choosing the hyperparameters that go into priors. But in this case, we can use this one. Questions?
I'm a little bit confused in terms of like how to understand like you use Poisson distribution to model like the upsilon, and how to understand, okay, so what is upsilon equals 50? What does it mean?
Okay, so again, if we go back to here, upsilon is just the sort of the integer by which we shift everything over with these Bell number things. So if upsilon is 0, then just, you know, all these go away and we get n choose x of the xth Bell number divided by the n plus 1 Bell number. But upsilon doesn't have to be 0. It could be 0, 1, 2, 3, any of those things. We still get valid Bell numbers. And so that sort of gives us a parameter space theta that we can think of upsilon living in. And that's the non-negative integers. And we've only learned like one probability distribution for the non-negative integers. So we kind of have to go with that one, at least for now. So this is going to result in like a valid usage of Bayes' rule, but it's kind of like trying to cook dinner when all you have is like a pineapple and ketchup. Like it's two valid distributions that you can combine together to get a probability distribution. It's not necessarily going to make the most sense. If I have more probability distributions, I could, you know, possibly come up with something different. So anyway, we have upsilon. We know it's a non-negative integer, and we have one distribution that we could use for non-negative integers. That's the Poisson. So we're going to go with it. All right. And we just saw what the Poisson probability mass function is. It depends on one hyperparameter mu, which you are going to have to choose to express your beliefs about upsilon before you start seeing the data. But if you just you know, work out what the expectation is and make a plot like this, we see the expectation of what happens on the first roll of a frame of bowling is a decreasing function of upsilon. So that's why I said you can interpret upsilon as how uncoordinated a person is. And we want to estimate that level of uncoordinatedness for a particular person. And we might see, okay, well, I think this person, you know, is capable of averaging like 7 on their first roll. And so I just go from 7 over the curve down to 50. That tells me, you know, for somebody like that, I should expect upsilon to be about 50. And so I could choose mu accordingly. And it doesn't have to be exact because the variance is going to be 50 as well. So that's like a standard deviation of 7. So, you know, it could easily be within like 15 of that. But anyway, that is sort of how I might think about doing something along those lines. Okay, so how do we use Bayes' rule? Let's say we have some data on 9 frames of bowling, because the 10th frame is a little bit weird. So let's just say we observe the first 9 frames of somebody bowling. How will we update our beliefs using Bayes' rule? So our posterior beliefs about the person's upsilon are given by Bayes' rule. So the conditional probability of upsilon given 9 frames worth of data that have 2 rolls on each frame, unless it's a strike, in which case the second roll we'll just call it 0, and mu, which was our initial expectation for what upsilon is. That is left-hand side of Bayes' rule is equal to the right-hand side of Bayes' rule. And the right-hand side of Bayes' rule has 3 components. The first is the prior probability of upsilon given mu, which is just going to be our Poisson PMF, which we derived before. And then the next question is, well, what expression would we use for the probability of these 9 frames of bowling given upsilon? So what would that be? What would that be for the first frame? Sandra? Mm-hmm. Right. Right. So marginal probability for what happens on the first roll of the first frame times the conditional probability distribution for what happens on the second roll of the first frame. So that would give us a probability for frame 1. And then it's the same thing for frame 2. And frame 2 is independent of frame 1. And all the frames are independent of each other. So how would we get an expression for the probability of all or almost all 9 frames? Sasha? Yeah. Big J is 9. I didn't do 10 because the 10th frame is weird. So let's just say we got bored after 9 frames and left. What would be our expression for the probability of what happens on 9 frames? Say the joint probability of what happens on 9 frames. Nine independent frames. Each of which we know an expression for the probability of. Nick? Multiply them together. So using the general multiplication rule, in the case of 9 independent frames, although the 2 rolls within each frame are not independent of each other, so you have to take marginal on the first roll times conditional on the second. But you can do that for all 9 frames, and you can multiply all that together to give you a joint probability distribution for what happens on 9 frames. So we've got a prior probability mass function for upsilon, which is a Poisson. No name thing, but we just multiply 18 things together to get the probability for 9 frames of bowling. And then the last question is, what is the probability of 9 frames, or what happens on 9 frames of bowling in the denominator, irrespective of upsilon? How would we calculate the denominator piece? Conceptually, you don't have to calculate it by hand. Gotta have 3 pieces to use Bayes' rule.
The probabilities, marginal and conditional amount is right. Well,
Ignoring is not the word I would have used. How about marginalizing over? Okay. So remember before we talked about how would we get the marginal probability for what happens on the second roll of a frame of bowling? What did we do to get that? Remember we had the table? Summed. So we took the joint probability of the first roll and the second roll, summed it down to get the probability of what happens on the second roll, irrespective of what happens on the first roll. So now if we want the probability for what happens on the first both roles of 9 frames of data. What we do is we take the distribution of upsilon and the data jointly and sum it over upsilon to purge that out, leaving us a function of the data alone. And so the denominator in Bayes' rule, it's just the numerator summed over all possible values of the unknown discrete parameter upsilon. So we just marginalize out upsilon from the joint probability of upsilon in the data. We're left with a function of the data by itself. Just the same way we got the joint probability for what happens on 2 rolls and summed over all the things that could have happened on the first roll. And that leaves us a function for the probability of what happens on the second roll. So by summing over all possible values, we can purge something out of a joint distribution, leaving a marginal distribution of the other thing left over. So how would we do that in practice? Or maybe some more math. So the denominator there can be thought of as the expectation of some g function of upsilon, where the g function is the conditional probability of the data given upsilon, and we're weighting it with the prior probability function. And so g is what's known as the likelihood. It's considered to be a function of the parameters because it's only going to be evaluated at the observed data. But like any function, we can take its expectation by doing a sum over all possible values of the probability weighting on that function. So in this case, we're summing from 0 to infinity, which sounds like it would be a whole lot of work. But in practice, when evaluating an infinite sum numerically, you just stop once the terms start getting so close to 0 that you don't care about them anymore, or your computer can't distinguish them from 0. So we have this probability of the 9 frames given upsilon, and that's just for each frame what happens on the first roll marginally times what happens on the second roll conditionally, multiplied from j equal 1 to j equal 9 if we have 9 frames. So that's our function that we want to get the expectation of. We're weighting it with our Poisson prior PMF, and we're summing it over all possible values of upsilon, which are the integers from 0 to infinity. But eventually, we start adding like basically 0 onto the sum, and then at that point, we can just stop. So what it looks like in practice, you would set mu to whatever value you think is appropriate before you start observing the data, let's say 100. Set up your parameter space, theta. In this case, if you try to do it for any values of theta bigger than 207, your computer will blow up. So don't do that. So we'll just limit it to 207, but that's going to be fine. It has no probability of getting that high anyway. Our prior probability can be represented by the Poisson PMF, which is given by the dPois function in R. So we give it theta and mu. We get back 208 probabilities, 1 for each level of theta, and given our assumption mu. And the probability mass functions in R all start with the letter D for reasons that might become clear later, eventually, not today. Anyway, that's our prior probabilities. And then we just have to multiply that by the probability of the data given upsilon for each of those 208 values of theta in order to get the numerator of Bayes' rule. And that is most easily accomplished using the s-apply function, which you might not already be familiar with in R. The s-apply function takes 2 main arguments. The first argument can be like a vector or a list or whatever. And the second argument is a function. And what s-apply does is it applies that function to each element of the vector or the list or whatever that you give it as the first argument. So it's going to apply the following function to each element of theta, which is the integers between 0 and 207 in this case. So we'll just index those by I, and we'll calculate the probability of what happens in a game of bowling. Game is not really the right word because we're ignoring the 10th frame, but the first 9 frames of bowling, we're going to take what happens on the probability for what happens on the first roll of each frame, and then multiply it by another s-apply thing, which gives us the conditional probability of what happens on the second roll of that frame. Multiply those 2 things together. That gives us the probability for what happens on the ith frame. And then we do prod of those to multiply those 9 probabilities together to give us the probability for this or that happening on a game of bowling, excluding the 10th frame, for each of the 208 values of theta that we are considering, 208 being basically appropriate for infinity. And then once we get the numerator of Bayes' rule, all we have to do is divide by the sum of the numerator across all 208 values to normalize this so that our posterior probabilities add up to 1. Remember, always when working with probability, got to make sure your probabilities add up to 1. Otherwise, you've done it wrong. But if they do, then you've most likely done it right. And then we can look at the plots of those 2 things, or we could summarize them numerically. And in this case, with these 9 frames of bowling that I had here, it comes out like this. So we have on the top here bar plot of prior probabilities for what upsilon could be, given that our expectation going into it before we saw the data was mu equals 100. And the Poisson distribution with large mu is a very symmetric looking thing. And it looks like this thing in red here. But when I condition on 9 frames worth of data, then my beliefs go from the marginal prior probability distribution that I use for upsilon to the conditional probability for upsilon given the data and what I believed at the outset. And you can see by conditioning on 9 frames worth of actual data, the distribution of probabilities has scooched to the left. They go from prior to posterior by conditioning on some actual data. So it turned out that these frames of bowling would suggest that whoever this bowler is less uncoordinated than what I thought originally. Now, it didn't move all that much because I only observed 9 frames of bowling, not a whole lot of data. And so if I have reasonably strong beliefs going into it, it's not going to affect the posterior probabilities all that much, but it does by a noticeable amount. And if I saw like, 100 frames of bowling by this person, I could pretty much move the posterior probabilities to, anywhere, irrespective of what I believed going in, if I observe a moderate to large amount of data. Here, just a small amount of data, but enough to see the movement. So going from a marginal prior probability on upsilon to a conditional probability of upsilon given the data and mu, that's what using Bayes' rule is really all about. Updating our beliefs about the unknown parameters given known data that we observe. Questions about that? Yes, Sandra?
If you're doing the experiment, you wouldn't actually collect specific parameters.
Not quite sure I understand.
If the function that you're selecting for so if you were conducting
Right. So essentially, you could, in principle, say, I know upsilon is 78 and go from there. That's equivalent to having a prior where the probability that it's 78 is 1 and anything else is 0. So technically that is legal. It's a little bit on the dogmatic side. So irrespective of how much data you observe, you could never change your beliefs to upsilon as something else. But you could do it within Bayes' rule. What's more common is to say I have a distribution, I think it's mu, but I acknowledge the possibility that I acknowledge the reality that I'm uncertain about it. And I want to use data to have a different and more certain set of beliefs after conditioning on the data. And that's what we see here with the green. And so the posterior probabilities are really the answer. But the answer is a function rather than one number. The answer is a set of probabilities over everything that could happen, everything that upsilon could be. And so when dealing with something that you don't know, like who's going to win the Super Bowl, the Patriots or the Rams, before it happens, it's both. But it's both with some probabilities. And so when trying to reason about something that you're uncertain about that happens in the future, you have to consider it could be any of these things. Upsilon could be any of these things. But it's not like all of these things are equally likely. It's more likely the Patriots beat the Rams. It's more likely upsilon is like 95-ish than 207. And so everything has to be weighted according to its probability. And the probabilities you want to use are the probabilities given the data that you have. Other questions? So let's learn one more distribution. Hyper geometric distribution. Even more hyper than the geometric distribution, which we have in left. The geometric distribution is kind of boring, so let's just skip straight to the hyper geometric distribution. So recall the binomial distribution, which we started out talking with today, corresponds basically to sampling with replacement. Each of the n values has the same probability of being. The fact that the first one came up as success doesn't affect the probabilities of any of the others. Hyper geometric distribution is the distribution you want to use when you're thinking about a sampling process without replacement. So by taking one success or failure or whatever it may be out of the set, now you change the probability for your next draw from that set because you didn't replace it. And the hypergeometric distribution has a probability mass function depending on nk and little n that can be expressed as a ratio of choose functions. So n is the size of the set that you're drawing from. K is the number of successes in that set. And little n is the number of times you're going to draw from that set without replacement. So you draw the first time, keep it out, draw the second time. For the second time you draw, the probabilities changed relative to the first time you drew because your set changed. So if we have a shuffled deck of cards and you deal like 2 to yourself, what is the probability that those 2 cards are going to have the same value? How would we work out what that is?
Not entirely sure how many different kinds of cards are in a typical card deck here, but
13.
13 different. So would it be, so each trade has 4.
Mm-hmm.
So it would be, and it's 52 cards. So it would be 4 divided by 52 times 3 divided by 51. And then you can do that with 13 different types of cards, so you would multiply.
So you can sort of think about that intuitively, or you could just query the probability mass function for a hypergeometric distribution, which will tell you the probability of getting like 2 aces, but probability of getting 2 aces is the same as 2 kings and 2 of anything else. So there's 13 different ways of doing that, but the probability of getting a pair of, you know, any 2 values is 4 times 52 times 3, or 4 divided by 52 times 3 divided by 51, because when you get the first ace or whatever, then there's only 3 aces out of 51 left. But that's just a special case of a hypergeometric process. If I had a set of big N things, of which there are k successes in that set of big N things, and I took a little n draws from it without replacement, what would be the probability that I get, you know, x successes when I don't do replacement? Well, that's given by the hypergeometric PMF. But, you know, the cards thing is just one special case of that. Okay, so that's all for today. I will post the first homework on Canvas tonight. It will be due a week from today before class, and I'll have instructions on, you know, how to upload it and things like that. If you don't already have it, you need to get RStudio, and even if you previously had RStudio, you need to get the preview of the next version of RStudio. Technically, you can use any RStudio you want for the first homework, but going forward, when we start to use Stand, you're going to need like the newest version and not even yet released version of RStudio, just the preview of it. So I will post instructions on how to do that on CanvasWire, which if you're not already signed up for, you needed to have been signed up for like a week ago. Questions? Okay, I will see you on Tuesday.
Yeah,